Okay, session 5. This session is going to be on optimization of binary linear classifier. Okay, optimization of binary linear classifier. Now, what we were looking at was solving the binary linear classification problem, which we sort of said involved determining the best linear decision boundary for the given training data. That was our binary linear classification problem. And we said that problem would be solved with an optimization approach. And before we jumped into that, we said that we would take a brief detour. We would take a detour and discuss the general ideas behind optimization. And in particular, we looked at one type of optimization called the gradient descent algorithms. Right? So we looked at gradient descent algorithms in the previous lecture, and now it is time for us to apply those ideas to the binary linear classification problem. Great. So to quickly recap, here is where we were, right? I mean, when we stopped talking about the binary linear classifier. Our job or our target was to find the best linear decision boundary, W transpose X, these are vectors, W transpose X is equal to 0. And over here, what I have done is I have added W0 to the vector W. So the vector W is going to look something like this all the way, and finally I'm going to add W0 at the end. And the vector X are the values of the feature variables for each point in the training data. So x1, x2, and I'm going to add 1 right at the end, right? So instead of writing W0 separately, you remember the notational change that we made, where W0 was included in the vector W, and we appended a 1 to the vector X, right? So this is the notation that we are following here. So our task, we said, was to find the best linear decision boundary, W transpose X equal to 0, in the space of feature variables, such that for the training data, maximum points from one class are on one side and other class on the other side of the boundary, right? And this word best, the word best was what triggered the entire requirement for optimization, right? Or words like maximum points on one side, etc. So those were hints to us that this is clearly going to be structured as an optimization problem. We also sort of have been looking at this problem, and we've told ourselves that this is the problem involves finding the hyperplane. W transpose X equal to 0 is a hyperplane such that as far as possible, W transpose X is greater than 0 for one class in the training set, and W transpose X is less than 0 for the other class in the training set. Remember, this is a binary classification problem, so there are only two output classes. Out of the training data, some points lie in one class, some points lie in the other class, and our job is to basically find this hyperplane that best does this, that best sort of segregates the points in the two different classes in the training set. So again, that's a clear hint right there. As far as possible, the words like these are a clear hint that you have to set this up as an optimization problem. Okay, we took a detour in the previous lecture and discussed some of the general optimization ideas. That was an important lecture, and it sort of helped us get a grip on how optimizations are structured in general, right? And we said that one specific type of metric that is used for optimization is the error itself, right? So if we are able to define the error as a metric, then error minimization becomes a reasonable goal to find the best possible solution. Okay, and using error as a metric basically worked as follows. We had to define the error that had to be minimized, right? Define the error function that represented the error that you had to minimize. Then we would find the gradient of the error function at the point where we were. Gradient of the error function. We relied on calculus to sort of tell us how to find this gradient. And then we said that we would take a step in the direction of the negative gradient. Take a step in the direction of the negative gradient to move to the new point and thereby reduce the error. And if we kept doing it iteration after iteration after iteration, our hope was that the error would be suitably minimized and we would end up at the best possible solution. So this was the general framework, the mental framework we kept in mind while approaching the optimization problem and configuring it as a error minimization problem. Okay, this was an important slide in the previous lecture and I'm going to sort of bring it in here as well. The reason why error as a metric works in many problems in AI is because of what we are essentially trying to do, right, in AI problems. What we are trying to do in AI problems is that we have training data, and we are trying to build mathematical models. We are trying to build mathematical models that best replicate or that best mimic the behavior that you have observed in the training data, right? So you have training data, which is basically observations, feature variables, observed output, and so on and so forth. And what you want to say is that you are building a mathematical model that mimics or replicates this input-output behavior, right? So given a particular input, you would like to see the output, you would like to see the model return an output that replicates or mimics as close as possible the output that you observed in the training data, right? Now your mathematical model clearly has certain parameters, certain knobs or certain controls that you use, that you can tweak around, that are under your control, whose values you can select or whose values you end up selecting, right? And the behavior of the mathematical model, the input output behavior of the mathematical model depends upon the values of these parameters that you choose in your mathematical model, right? So now when you're talking about optimizing the mathematical model to best replicate the behavior observed in the training data, what you're effectively going to do is select the best values of W1, W2, W3 and so on that allow you to achieve that best replication of training data, right? So that's what we are talking about here. Okay, I also showed you an example, and what this example said was that you had training data, right? And these are the feature variables. These are the feature values of the feature variables for your first training data point, for your second training data point, and so on and so forth. And we said that, you know, if you were to give this input to your mathematical model, the output returned by the mathematical model was going to be something. I mean, you would run this model and it would return you a certain output, whereas there would be an output that you had recorded during the process of capturing training data. And the difference between these two, the difference between the output returned by your model in response to your input and the actual output you recorded while recording the training data, the difference between these two was the error, right? So the error, again to repeat, the error was essentially the difference between the output returned by the model for certain values of W, and the recorded output when you gathered the training information, right? So this was the error. So similarly, you would observe certain error for the second training data point, for the third, fourth, and so on and so forth. So these were our errors, right? So and the error would differ depending upon your choice of the parameters of the mathematical model, the W1, W2, W3 and so on. So therefore the optimization problem was structured whereby you would have to select the best values of the W's, so that these errors are minimized. And to sort of take a combined view of all training data, you did a summation of errors. So you did a summation of the errors. You did a mean square error type of an approach over all training points, right? So you summed it up, right? So that was the general idea. The case of the binary linear classifier is a little bit different. Okay, and let's see why that's a little bit different. In the binary linear classifier, what happens is that you have only two output classes, A and B, and without loss of generality, you could call them as yes, no classes, right? Two classes, so you can, without loss of generality, one class is a yes. You could ask the question such that one class returns an answer yes, the other class returns an answer no, right? And what you have as observations in your training data is that for each training data point, your recorded output in the training data is either a yes or no. Right? So earlier you had numerical values. In the previous lecture we considered a general problem where there were numerical values. Now you have yes, no, right? And the mathematical model that you construct also returns a yes or no, right? Because you have to sort of, this is a binary linear classifier. You have to classify into one of those two classes, right? So in a crude sort of way, I could say that these are booleans, right? I mean, for those of you who are technical, who have like some little bit of programming knowledge, these are like sort of boolean as opposed to the real numbers that you saw earlier, right? So in the more general case, your outputs could be, floating point general numbers, right? Whereas for your binary linear classifier, these are sort of boolean, right? So how do you exactly define the distance between a yes and a no, and so on and so forth, right? So it's not as easy as just subtracting and adding up everything. So you have to be a little bit more careful. You have to be a little bit more careful in your choice of error definition, right? Okay, so mean square error is not suitable. I mean, what is the definition of mean square error between two Boolean quantities, right? So mean square error, let's straight off the bat agree that mean square error is not suitable. Okay, and therefore we have to look for other metrics for error. Okay. For most optimization problems, like I said, for most optimization problems, the crux of the matter lies in selecting the best error function, right? Or using the best metric to optimize. Remember, I had that list of things that you sort of need to keep in mind when you're approaching an optimization problem. The first thing is to select a good metric. Okay, and that metric may differ from problem to problem. Even for a particular problem, you may have choice of metrics, right? So this lecture is now going to focus on exercising that choice of error metrics. We will look at what sort of error metrics are available to us for the binary linear classification example, okay, and then select one of them, and the rest of the approach will probably remain the same. I mean, it will remain the same. So we are going to devote some time now to selecting the right error metric. Okay. One commonly appearing error metric, it's instead of error function, it's also called a loss function, is the 0-1 loss function. Okay, let's understand what the 0-1 loss function is. I'm going to be throwing some terminology at you simply because I want you to know what these terms mean. Okay, let's see what the 0-1 loss function is. Now, remember our model, the computed value is yk equal to w transpose xk. And then in the classifier, we sort of classify a particular point. Our model classifies a particular point based upon whether this is greater than 0 or less than 0, right? So the computed value score is, you remember we had said, where does this W transpose xk come from? Remember we said this is W1 x1 plus W2 x2, so on and so forth, Wn xn plus W0, right? So this equal to 0 is the hyperplane, and if this is greater than 0, we classify on one side. If this is less than 0, we classify into the other class, so on and so forth. So this is W transpose x. This would be the computed value for certain values of W, right? This is the computed score. Expected value, Now this is a slight change. See this carefully. The expected value we define as zk for a particular input k. Here also yk is w transpose xk, where xk is particular input. K will be the running variable over all your training data. So if your training data has m points in it, k would go from 1 to m, right? M points in the training data, right? For each of this training data, you also observed what the output was, and that is your expected value zk. Zk or zk is the value that you observed for training data point k, right? And we are now saying that it can either be 1 or -1 depending upon the class. Okay, so we have started assigning numerical values to those booleans. Okay, either +1 or -1. You will say, why not +5 and -5? That's fine. We have to select some number, and we will select +1 or -1, right? So we will assign a +1 if the expected value is going to falls in one class, -1 to the other class. Numerical values for the booleans. Okay, we define a quantity margin. Okay, this is often used terminology. And the margin essentially is a measure of how correct we are. Okay, and it's defined as margin equal to yk multiplied by zk for the training point k. Okay, for each of the training points, therefore, we compute the margin. We are able to compute the margin, and it is yk multiplied by zk, where yk is this, right? So what does yk multiplied by zk really indicate, and why is it an indicator of how correct we are? Let's understand that. So yk is what you computed, right? Yk is what you computed. Zk is the expected thing, right? Now, if your computed score was highly positive, if it was highly positive and your expected value was also +1, okay, if your expected value was +1, what it means is that yk multiplied by zk is a highly positive, a large positive quantity, and therefore it indicates how correct you are, because you were expecting +1, your model returned a very high positive quantity, and therefore you were absolutely right. You were correct to a very high extent. That's the logic, right? Similarly, if your computed value was a very large negative number, a highly negative number, and your expected value was -1, same thing. These two minuses would cancel, and yk multiplied by zk would be a very large positive quantity. Again, saying that you were expecting a -1, the model returned a very, very high negative number, and therefore you did a good job. On the other hand, if your computed score was a highly positive value and your expected value was -1, the margin would be a very large negative number, okay, a highly negative number, which tells you that you are absolutely wrong. I mean, you were supposed to get a +1 and your computed value was a very, very high negative number. Clearly, you were doing a disastrous job. Right? So the margin, if you can now understand why this is this way, expected value multiplied by the computed score, if they both have the same sign, your margin, which indicates how correct you are, would be good. And if they have different signs, depending upon the magnitude of your computed value, you would either be very wrong or slightly wrong, and so on and so forth. Right? So margin is an important terminology, indicates how correct you are. Loss. This is the loss function. Okay, it's called the 0-1 loss function because its output value is either a 0 or a 1. And the loss function basically says is 1 if yk multiplied by zk is less than 0, if yk into zk is less than 0, and it is 0 otherwise. 0 otherwise. Okay, so if your computed value had the same sign as the expected value, then your loss is 0. You were correct, and therefore your loss is 0. And if you made a mistake, if your computed value was of a different sign compared to your expected value, loss function has a value of 1, okay, and the overall loss function is simply the summation of the individual losses, over the set of training points. K goes from 1 to m, right, where m is the total size of your training data. Now what this just says is the loss function is basically the count. It's the count of training points on which you made a mistake. It's as simple as that. I mean, we went through all the terminology because the terminology is important. We will keep referring to the loss function, the margin, etc., etc. And you may read other books, you may run into these definitions and you don't want to sort of blank out on what these things mean. And therefore, I introduced the terminology. But essentially, the loss function, while talking about the binary linear classifier, is simply the count of mistakes over training data. So if your training data had 2,500 points, out of which on 1,700 points you made an error, the loss function would have a value of 1,700, and the other 800 points, the remaining 800 points you did correctly, so you would not count them, right? So this is the loss function, definition of the loss function. So the question that arises is, this is a simple-minded thing that, comes to mind. And can this be used as a good metric for the binary linear classifier? Because it makes eminent sense. Just minimize the number of points on which you made an error, minimize the loss function, right? It's a very logical thing to think about. So let's try to answer that question. Is the 0-1 loss function a good error metric to be using? That's the question, right? It sounds pretty logical. Is it a good one to use for our problem? So the 0-1 loss function looks like this. I mean, on the x-axis what you have plotted, is yk, right? So if yk is less than 0, the loss function returns a value of 1, and if yk is greater than 0, it returns a value of 0. Right? This is what we saw in the last slide. Essentially, I mean, I've drawn this figure that we saw a few lectures ago. Let's say this is the blue side of things, this is the blue side of things, this is the yellow side of things, and the loss function basically, for every point that's on the wrong side, 3 yellows are on the blue side and 4 blues are on the yellow side. Sorry, so 3 yellows are on the blue side, 4 blues are on the yellow side. So the value of the loss function here would be 7. But for each individual point, the way we calculate the loss function is if yk multiplied by zk, this is multiplied, yk multiplied by zk is negative, the 0-1 loss function returns a 1, right? So just count the total number of mistakes you made. This is the proposition. What we observe is that this function, this 0-1 loss function, has a 0 gradient everywhere, right? I mean, there is one point of discontinuity that you ignore, but the value of the 0-1 loss function remains constant everywhere else, right? And therefore it is not useful for gradient descent. Remember, the whole idea of gradient descent was to find the derivative and use that gradient to tell us the direction in which you want to move in. And if that gradient is going to be 0, we are not going to get any sense of where we need to move, how we need to modify the values of the w's to minimize the error, right? So using a error function that has a 0 gradient everywhere is not a good idea, because it does not satisfy the second requirement that we talked about in selecting the metric, right? We said that in an iterative mechanism, at every stage we need to get some indication of how we select the next point, of how we modify these parameters to minimize that error. And if your gradient function if your error function has a 0 gradient everywhere except at one point, it therefore cannot be a good choice of error function, because you're going to have a zero gradient. I mean, the gradient descent is not going to work, right? So therefore the 0, 1 loss function as it is not a good error function to choose, right? So what do? We look for another error function. So we are going to investigate the hinge function as a possible loss function. Okay, this is a good candidate to check out how well it serves us as a loss function. So what is the hinge function? The hinge function basically looks like this. Okay, the hinge function here I have plotted on the x-axis. I have plotted yk, okay, which we used to call the margin, right? The margin. The margin was an indication of how correct we were in our classification. So the way the hinge function looks like, I mean, as you can see, it looks like a hinge around this point 1, and these two are sort of panels of the hinge, right? So that's why it's called the hinge function. What the hinge function says is that if yk zk is greater than 1, the loss or the error is going to be treated as 0, whereas if the margin becomes lesser and lesser, your loss is going to increase. And the hinge isn't around the point 0, it's around the point 1. So what you're effectively saying is that as the confidence in your answer starts becoming less and less, once it starts going below 1, you would like to start imposing a penalty. Okay, so that's what the hinge function is saying. Mathematically, the hinge function can be written as 1 minus yk times zk. That's basically this graph when yk zk is less than 1 and 0 otherwise. Okay, and of course, let's keep in mind that yk is simply w transpose xk, right? So this is how the loss is defined for a hinge function. Okay, and you can actually compute the gradient of this. So the gradient of the hinge function is minus zk times xk. Now zk is a scalar, it's either plus 1 or minus 1, and xk is a vector, your input vector, your kth input vector. So the gradient is this when yk zk is less than 1 and 0 otherwise, of course. I want to spend a minute looking at this hinge function in a little bit more, detail. So let's consider this two-dimensional example where we have to classify the blue dots and the yellow dots. And let's say this right side is the correct side for the yellows and the left side is the correct side for the blues. And this ended up being your decision boundary, right? So this was your decision boundary. Okay. What the hinge function is really asking you to do is draw two parallel hyperplanes, lines in the case of 2 dimensions, two parallel hyperplanes to your decision boundary. Okay, so these are two parallel hyperplanes. Okay, and what the hinge function is actually telling you is that if a blue dot is to the right of this blue line, okay, if the blue dot is to the right of this blue line, you start imposing a penalty on it. Okay, similarly, if a yellow dot is to the left of this yellow line, you start imposing a penalty on it. So it's not saying that you basically only impose a penalty on the points that were incorrectly classified. Okay, so that would have resulted in your hinge being at point 0. What it is saying is that give some more margin. So you are actually going to start imposing a penalty on not only the points that were wrongly classified, but also the points that were barely correctly classified. In other words, the points for which the margin was positive, but smaller than 1. I mean, 1 has been chosen arbitrarily, but it indicates to you, I mean, it could have been chosen to be anything else. But what it tells you is that you are going to start imposing a penalty. You are going to start counting the loss when your margin actually goes below 1. Okay. So for example, this point, although it is correctly classified, would still contribute to the loss. These points would not contribute to the loss. Similarly, these yellows would not contribute to the loss, but this particular yellow would contribute to the loss. Okay, so that is what the hinge function is doing. It is not only imposing a penalty on the points that are wrongly classified, but it is also imposing a penalty on points that are just barely correctly classified. Okay, so in other words, using the hinge function as a loss function, you would want all the blue points. Your desire is to see all the blue points well to the left of the decision boundary. Okay, even beyond this dotted blue line. Similarly, you would like to see all the yellow points to the right of this yellow dotted line. Okay, not just to the right of the decision boundary. So that is what the hinge function as a loss function is attempting to do. Let's look at how gradient descent would work if you were to use the hinge function as a loss function. Okay, it would work exactly like any other function. Okay, we just saw on the previous slide that the hinge loss, and now you are sort of summing it up over all the k's where yk, zk is less than 1, right? So the total loss, the total hinge loss is the summation over k over only those points for whom zk was less than 1. In other words, for whom the margin was less than 1. Okay, and the points where the margin was more than 1, you just ignore their contribution to the loss, or the contribution to the error is going to be 0. And when you take the gradient of this, the gradient is going to be this. Okay, the gradient is simply this. You take the gradient of the loss, this is going to be your gradient. Again, there is a summation over only those points where yk, zk is less than 1. Okay, so given that this is your gradient, here is what your iterations are going to look like, right? I mean, your your new weights are going to be your old weights plus because there is a minus sign in front of these gradients, right? So there is this minus, and you want it to move in the direction of the negative gradient, so those two minus signs cancelled each other to give you a plus. Alpha is the small step size that we've always been talking about, and then the gradient comes over here. Okay, and this is summed up over all the k's where your margin was less than 1. Okay, your denominator, notice, is still m, right? I mean, it's the total number of points in your training set. So this is what your this is how you're going to calculate your new weights based on your old weights. So for example, your W1 would be W0, which is, let's say, the initial values you began with for W. Let's say you just selected them in a random fashion, either all zeros or all ones. I mean, ideally better to, not have zeros or ones. I will have more to say about how to choose your initial point in just a minute on the next slide. But this were your initial weights, and your W1 was simply W0 plus this thing, and this summation would run over all those points for whom the margin was less than 1 when these values of W, when W0 was used. Okay. Similarly, W2, I mean, once W1 was calculated, W1 would come here, and W2 would be W1 plus this quantity computed using W1. Okay, so on and so forth. And then, you keep running your iterations. Let's say W957 equal to W956 plus this thing calculated by inserting W956 in your model. Now, some of you may take a look at this. Some of you may take a look at this gradient and say, hey, is this constant? Is this independent of the values of W? Because I don't see a W in there. Okay. I'll give you a minute to think about the answer to this question. But let me go ahead and give you the answer right now. I mean, if you want to pause the video, that's fine. Although this term does not explicitly have a W, note that the points K, the K points over which this summation happens will change upon your selection of W. So when W changes, the points for which the margin is less than 1 change. Okay, so this summation happens over a different set of points every time. Okay, as your W changes. So therefore this term is not constant for all iterations. It actually changes depending upon the value of W you're using in that iteration. Okay, so that was the hinge function. We are going to sort of, talk about another error function very briefly. This is called the logistic loss function, and it is defined as follows. This is the definition of the logistic loss function, okay, right here. And as you can see, it doesn't have a point of discontinuity. This is a continuous function. Its gradient can be computed, and you can exactly run the same gradient descent that you ran earlier by computing the gradient at every iteration. Okay, the thing about this particular loss function, which is slightly different from the hinge function, is that it continues to impose a penalty, smaller and smaller penalty, even as your yk zk goes beyond 1. I mean, even if your yk zk is more than 1, there continues to be a penalty imposed on those points as well, albeit a small penalty. It's a small penalty which goes to 0 very quickly, tends to 0 very quickly. But what effectively this logistic loss function will try to do is make sure that your points are pushed further and further away from your decision boundary, or in other words, calculate a decision boundary so that your points are as further away from the decision boundary as possible. Right? So that is what the logistic loss function is going to attempt to do. Okay. So now let's sort of understand what the gradient descent for the binary linear classifier is. We define the error function as always, called a loss function in these cases, to be minimized. You could use the hinge function. You could use the hinge function or the logistic loss function. Two good candidates. You could use one of them as the loss function to be minimized, right? The mean square error, etc. are not good candidates. The 0-1 loss function is not a good candidate. You can select the hinge function or the logistic loss function, define the error to be minimized, evaluate the gradient of the loss function, which we saw, the standard approach to solving the gradient descent problems. Take a step in the direction of negative gradient to modify the weights. Take a step in the direction of negative gradient to modify the weights. The weights are the coefficients of the feature variables, going back how the weights came into the picture. And we iterate to get the best decision boundary, right? So we keep iterating to get the best weights. The best weights are actually the coefficients of the hyperplane, and therefore if you keep iterating, you will get the best hyperplane, which is the best decision boundary. And it's actually been shown that it converges to a global minimum. If you use a function like the hinge function or the logistic function, it would converge to the global minimum, meaning that it would give you the best possible decision boundary. So here is the answer to the word best that we have been using in the last 5 sessions. Okay. I want us to do an exercise at this point. I mean, I have sort of told you how the gradient descent function can be used for solving the binary linear classifier. We also discussed a real life example in one of the sessions, session 3 if I am not mistaken. But at this point in time, I want you to leave you with an exercise. Okay. So these W's were the focus of our attention as far as optimization was concerned, right? The values of W's that define the best hyperplane, right? This was the entire focus of our exercise as far as optimization was concerned. Let us consider the example, the recruitment example that we took for this exercise. Okay. We said that our feature variables were going to be percentage marks, years of experience, annual salary divided by years of experience, joining period in weeks, distance to workplace in miles, number of languages known, etc., etc. Right? And the values of these feature variables essentially formed your feature vectors, right? So these were your feature vectors for each candidate, and this was the observed output, right? So this was the exercise, this was the recruitment problem that we looked at. Here is what I want you to do. I want you to generate some data. First, generate some data which broadly satisfies the following. Okay. So choose units. These will have numerical values. As you can see, these feature variables will have numerical values. I want you to choose units. Each of these can have units such that all readings have roughly similar order of magnitude. So for percentage of marks, typically percentage of marks may go from 40 to 70 or whatever, depending upon how the grading is done. But I want you to divide it by 10. So these numbers go from, let's say, real numbers go from, let's say, 4 to, maybe 7. For the years of experience, I just want you to take a log to the base 2. And depending upon what sort of candidates have applied, again, these would be real numbers less than 10. Similarly, the annual salary in lakhs divided by years of experience. This is a ratio. Let's just keep it as is. Joining period in weeks. Let's calculate the joining period not in days or hours. Let's tabulate it in weeks. Distance to workplace. Let's use miles instead of kilometers or meters or centimeters. So that again it lies roughly small positive numbers. Number of languages known. I wouldn't expect you to run into a guy who knows 40 languages. Typically 1, 2, 3, 4, whatever. So if you use these sort of units, the values of the feature variables would typically be real numbers less than 10. So, same order of magnitude. That's what I want you to do. I want you to generate data. Such that all of these are same order of magnitude. I want you to generate data where x1 and x4 are most important, right? Okay, so I want you to generate data where, let's say, the recruiter gives excessive importance to the percentage of marks and the joining period. He wants people with high percentages and who stay nearby to join quickly. Who can join quickly to get special weightage, right? I have colored some of these variables as red. And higher values of red here support rejection. Okay. So these are, in a way, annual salary in lakhs, joining period in weeks, and distance to workplace in miles. You want the values of these variables, you prefer the values of these variables to be as less as possible while making your recruitment decision, right? So higher values support rejection. And the green features, this doesn't look like green, but it is green. Consider this green: x1, x2 and x6. Green features are such that higher values support acceptance, right? So if x1, x2 and x6 have higher values, that would support the case for selecting a candidate. Let's say x1 and x3 have smaller dynamic range. x1 and x3 have smaller dynamic range. So let's say your percentage marks divided by 10 and annual salary in lakhs divided by years of experience have a smaller dynamic range. All of them are essentially same order of magnitude, but even within that same order of magnitude, let's say these quantities had a smaller dynamic range. They took values in a very small range. That's the meaning of dynamic range. The exercise requires you to answer just this question. What can you guess? what can you guess about the signs and magnitudes of each of the final weights? So if x1 through x6 satisfied these conditions, if x1 through x6 sort of satisfied these conditions, what could you say about the corresponding values of final weights, right, which your optimizer would return, right? Now, the way to this exercise is to basically just stare at the problem. That's how I want you to do this exercise. I want you to stare at the problem and take a guess. Take a guess of what the values of W1, W2, W3, etc. would look like, assuming the following was true. Okay, and then you can run a simulation to generate some test data, assuming this is true, and see if your guess was correct. Okay, that's how I want you to do this exercise. Why is this exercise important? Why is this exercise important? This, getting a feel for the final answer, or sort of getting a feel for how an algorithm works or what your expected answer is likely to be, is extremely important in solving any problem. But having a feel for what your final answer is going to look like in an optimization problem is even more important, because it can help you to judiciously select the starting values of the W's, or the weights, the coefficients, right? So if you have a gut feel, if you know what your final answer is going to look like, begin with that as your initial values for the iterations. And if your guess was correct, it will dramatically reduce the number of iterations. It will help you to converge quickly. Okay. So that is why having a gut feel for any problem, or for any approach or any algorithm, how it works, is very important. Right? So if you looked at the problem, if you saw what the dynamic ranges were of various variables, if you saw if some of them would affect positively, some of them would affect negatively, and if you sort of factored in all of these things in your mind, and if you developed a gut feel for what your final weights are going to look like, their values and their signs, those you could use as your initial values when you begin your optimization iterations. Right? So even otherwise, here there is a very practical benefit to sort of having a gut feel for the problem, right? Even otherwise, if you were in 10th standard, you were sort of solving a 8th standard, you were solving a simultaneous equation where the value of 5 tables and 6 chairs is 1,000 rupees. The value of 2 tables and 9 chairs is whatever, 1,700 rupees. What is the value of 1 chair? Right? What is the cost of 1 chair? If you solved the simultaneous equations and you got an answer of minus 7,000, you should have some inkling, right? If the numbers look the way they do, you should expect the value of the chair to be something, right? You should have a gut feel. If your final answer after solving the simultaneous equations was minus 7,000, you should know that you are wrong, right? So that's why, even in the simplest of problems, having a gut feel, or before beginning the solution, having some idea of what your final answer should look like, is always a great thing to have, right? It's always a great thing to have. And I'll encourage all students to sort of develop a gut feel for every type of problem, so that even before you solve the question, you have an estimate of what your final answer is going to be. And if your final answer does not satisfy your estimate, doesn't mean that your final answer is wrong, but at least you can start thinking about, hey, am I making a mistake somewhere? Why did I go wrong? So on and so forth. It calls for closer examination. And that is how you develop your gut feel. That is how you develop your instinct for any problem, or for any algorithm, or for any type of solution. And this is what ChatGPT does not do for you, right? ChatGPT may give you Python code, but the ChatGPT will not help you develop an instinct for a particular problem. And that is really going to be your value in the future. Okay, what you bring to the table. Otherwise, ChatGPT, everybody has access to, everybody can write Python code hereafter. What value you bring to the table is your insight, the special insight, the special gut feel you have, and your ability to configure a problem and devise a solution. That is the value that you are going to be bringing to the table in the future, right? Okay, so that's the exercise I want you to do. Create data, see if your gut feel is correct, so on, so forth, so on, so forth, right? Okay, it's now time to summarize in 3 minutes what we have learned over the last 3 hours. Okay, we've taken a lot of time, substantially more time than what somebody would take in a course on linear classifier, or an online lecture and so on and so forth. But we delved into enormous amount of detail. We looked at every possible nuance. We looked at a real life example, and that was what differentiated the lectures that you went through from the other lectures you would find, right? But now it's time for me to summarize in 3 minutes what we've learned in the previous 3 hours. Okay, summary. A binary linear classification problem is a classification problem with only two output classes. It's a frequently appearing problem in real life. Invest or not invest, medically at risk or not at risk, okay, go or no go. Many type of classification problems fall into the binary linear classification type. Okay, solving the binary linear classification problem essentially involves finding the best linear decision boundary in the space of feature variables over your training set. So you have a training set, you have training data, and based on that training data, you have yes, no in the training data, and based on the training data, your job is to find the best decision boundary such that it separates the points in the two different classes, right? So that is the job of the binary linear classifier. You may begin with certain observed variables, and you may have to move to different feature variables in order to satisfy the requirements of the binary linear classification problem: linearity, normality, independence, etc., right? So do not use your raw observed variables as your feature variables. You may have to make that transition. You have to make a good choice of a loss function. A hinge loss function or a logistic loss function we discussed was a good loss function. And then we said that we would use the gradient descent algorithm to iteratively modify the values of the weights, the values of the coefficients of the decision boundary, so as to arrive at the best decision boundary. Okay, so your best decision boundary would be your best separation over training data for points lying in the two separate classes. And once you had that decision boundary, you said that given a test input that you had not seen earlier, you would evaluate it to find on which side of the decision boundary it fell, and you would then assign it to that particular class, right? So this is how your decision boundary would come in handy in dealing with future test inputs. So this was what we did over the last 3 hours. I hope you've enjoyed it. I hope you have had a good time. We will be moving on to a different topic in the next lecture. Till then, I wish you goodbye. Thank you.